Bismillahirrahmanirrahim. Assalamu alaikum. I welcome you all to the lecture number 8 for the course of Communication Technology. My name is Engineer Jafar Ali and I'm your instructor for this course. So as you all know that in the previous class we have concluded our discussion about amplitude modulation. We have discussed about its different types and different categories like double sideband with suppressed carrier, single sideband and vestigial sidebands. We have also done several numericals regarding this, and we have learned quite a lot about the formulas that are used in the amplitude modulation. Now focusing on the next topic, that will be angle modulation. And as you know that we have already discussed broadly the types of modulation, that one is amplitude modulation and second one is angle modulation, and there are two further subclasses of that angle modulation. The first category or the first class is known as frequency modulation. So keeping that context in mind, we are heading towards our next topic, that is frequency modulation. So today's lecture briefs is shown to you now on the screen. So the topic that we will be covering in today's class will be the frequency modulation. That what is frequency modulation, how does it actually work, the operation, the phenomena, the considerations, the parameters, all the features, the advantages, the disadvantages, all these things will be discussed in today's class, along with their two types. The first one is NVFM, that is narrow band frequency modulation, and the second one is WBFM, that is wide band frequency modulation. So we will be discussing these two classes as well of these frequency modulation in today's lecture, so stay hold. So we have already discussed that there are two subclasses or two subcategories of angle modulation. The first one is known as frequency modulation and the second one is known as phase modulation. So these are basically are the subclasses, and I have already asked you one question, that why do we categorize both of these modulation techniques, that is frequency modulation and phase modulation, into one class, that is of angle modulation? Why do we keep these two, and why not amplitude modulation is over here? Why these two are classified in this one single class of angle modulation? So this question still remains unanswered till now, and I hope that some of or one of you or some of you might be have any answer for that. I will be waiting for that answer, because you know that I have already told you that this question has 3 marks of its own, so you have to gain these 3 marks, and the time was before midterm. Anyhow, we will be focusing on frequency modulation in today's class. So frequency range for the angle modulation varies from 88 megahertz to 108 megahertz. So this is specified for the angle modulation, not just frequency modulation. This frequency range is specified for both phase modulation as well as frequency modulation. And now coming towards our topic that is under consideration today, that is frequency modulation. So I will also upload some theoretical portion and derivation portion in the notes section that you will be having on the portal. So just to explain you in a very simple term, frequency modulation is that type of modulation in which the carrier is varied in accordance with the instantaneous value of the amplitude of the modulating signal, keeping the amplitude and of the carrier fixed. So your amplitude will be fixed. You will be only varying the frequency of the carrier signal with respect to the amplitude of the input signal or your baseband signal or your modulating signal. So based upon your amplitude of your input signal or your modulating signal or your baseband signal, you will be varying the frequency of the carrier, not the amplitude, not the phase. You will just vary the frequency of the carrier, and this is known as angle modulation, as simple as that. I have shown you a diagram in the figure. You can see that the message signal has two peaks amplitude. The first one is +5 and the second one is, let's say, -5. So you see that and the carrier is the same for all of these, and the FM generated wave that we have generated, the modulated signal, you can see that whenever the amplitude of the message signal is high, the frequency is high, and whenever the amplitude of the message signal is low, that is -5, the frequency generated, the modulated signal, or the frequency of the modulated signal is very low. You can see that, let me show you. You can see that when this frequency is, this amplitude is 5 at this point, from here to here, so the amplitude will be high. You can see that the amplitude, the frequency is high, and when the amplitude is low from here to here, you can see that the frequency of the modulated signal is very much low. So this frequency change is due to the amplitude of the message signal. So this is known as frequency modulation. Let's talk about some of the mathematical portion, the derivational portion. I have given you this complete form of this, and a complete derivation will be available to you on the notes section. So let's consider that this f of t is basically your modulating signal or your baseband signal, in which this Vm of t, Vm is basically your message signal, and this is the frequency or angular frequency of your message signal or your modulating signal, and this Vc of t is basically the voltage of your, or your signal of your the amplitude of your the complete signal of your carrier signal, and this As of c is that is the amplitude of that signal, and this W of c is the angular frequency of that carrier signal. So if you modulate this carrier signal with the amplitude, the modulating signal, the frequency modulated signal that you will be getting will be this thing that I have mentioned you, this derivation, this equation. So you can see that there are several terms. I will explain each of these terms one by one to you, and I have also given and provided the derivation in the note section. I repeat again, so you do not have to hesitate to ask about the explanation of this equation. So the major terms that is involved in this equation, let's talk about that. The first one is A of c, that is the amplitude of the carrier signal. This is the angular frequency of the carrier signal. This k is the constant. This km of f is the constant for the frequency, and I will explain you that what is this m of basically this thing. M of f is basically this modulation index, and if this is f, means frequency modulation. This is the modulation index for the frequency modulation, and this is the angular frequency of that message signal. So the complete equation of this this frequency modulation standard FM signal is represented by, you can see this complete equation. So this is the complete equation for this one FM signal. So FM signal is represented by this one equation, in which A of c is the carrier, W of c is the angular frequency of the carrier, B is the beta, or you can say this is known as deviation. This B of s is nothing but the deviation, and deviation is the ratio of the change in frequency to the message signal. So this is a frequency deviation. This B of f is the frequency deviation, that how much your frequency is being deviated from the message signal as compared to the carrier signal. This is the ratio. So this sine 2 pi FM is basically the frequency of your message signal or your modulating signal. Now let's talk about the spectrum of this frequency modulation. When any of you basically modulate a signal with respect to a frequency, so you get if you recall the amplitude modulation, you were getting side bands, two side bands. One was upper side band and second one was lower side bands. Here in this frequency modulation, there is a small change. This is a quite of change. The first very big change is that the side bands. In amplitude modulation, there were only two side bands, but in frequency modulation, there may be multiple side bands. You are not only restricted to a single or two or three. There might be a 10 or this is not the limit, infinite sidebands. You will have infinite sidebands for your modulated signal. So but this is not restricted to some quite number. We always talk about significant sidebands. Let's say there are let's say 10 sidebands, but not always that 10 sideband will be useful. So what do you say? You say that okay, no problem, just tell me how much are the significant sidebands. Significant sidebands are those sidebands which have some upper level of threshold of the information. Let's say you have placed a threshold of 50%. Let's say you will only allow a signal or accept a sideband if it has 50% of the energy of the total power. Let's say the transmitter was transmitting at 10 kilowatt, so you will only accept those sidebands that has at least 5 kilowatt of power. If the power is not of a given threshold, you will discard it. So you always talk about a significant sidebands, that what is the energy or what is the power. Mostly we talk about energy. So what is the energy? If the energy is above a given threshold, you will accept it. In certain cases you will accept it, in certain cases you don't accept it. We will discuss that also when it comes to practical side of generation in the coming or fourth lectures. But to this point, to this extent of the course, assume that you are you have the ability to accept or deny. So you will have to place a significant threshold. If energy of a sideband has energy above that given threshold that you have fixed, so you will basically accept that sideband, and if it is not, you will discard it and say that it is not significant. So those you accept, those sidebands are denoted or termed as significant sidebands. I hope that this justifies you the concept of the significant sidebands. Now let's talk about the features of frequency modulation. So FM is a hi-fi. Hi-fi means high fidelity, just like you see Wi-Fi, and this is a Mi-Fi. So this is also termed as hi-fi, high fidelity. So since FM signal has constant amplitude signal, I've told you that there will be no change in the amplitude and phase. The only change in the signal will be of its frequency. So the signal to noise ratio for such system must be higher. So you can get a good SNR or signal to noise ratio as compared to the AM. And the frequency of frequency spectrum of FM is same as that of AM in case of NVFM. NVFM, we will talk about NVFM, but in general the number of sidebands of the carrier amplitude varies according to the modulation index MF, that is index for the frequency modulated wave. So let's talk about the parameters of FM. FM requires infinite amount of bandwidth for transmission, since the number of sidebands are infinite. So you will have to justify a limit of the sidebands, but it is not possible. So you will have to the requirement of infinite bandwidth, because the sidebands are infinite. So you have to place a basically bracket, or you have to place a door or a stopping point or a limiting factor to cater that problem. Modulation index is the term, you know, that the maximum deviation divided by the modulated frequency, delta divided by MF. This is the modulation index, and the power of FM is always constant. It is always constant, that is the square of the amplitude divided by 2. AC square, amplitude of the carrier signal, basically square and divide by 2. So this is the always the fixed power of this FM. Now let's talk about the major two classes of this FM. So there are two classes of FM. The first one is known as NVFM, that is narrowband frequency modulation, and the second one is known as wideband frequency modulation. So just to simply elaborate you, if the modulation index is less than 1, so your signal or your FM is said to be NVFM. I repeat again, if your index is less than 1, let's say 0.6, 0.7, 0.8, 0.9, or even 0.99, so if it is less than 1, you term this FM as NVFM. And if your the index of your modulation is greater than 1, so this FM is considered to be a wideband FM. Let's talk about this further. So in NVFM, the maximum modulating frequency is 3 kHz, and the maximum frequency deviation is 35 kHz. Means your signal can be deviated up to 75 kHz of frequency. But in wideband FM, you can see that the maximum modulating frequency is 30 kHz to 15 kHz, 30 Hz to 15 kHz, and the maximum frequency deviation is still the same. So the only difference is of the maximum modulating frequency spectrum. In NVFM this was 3 kHz, and in wideband FM your input was to be varied from 30 Hz to 15 kHz. We have a large range of modulating frequency, and bandwidth of WBFM is 15 times of that of NVFM. So if you talk about NVFM, it has the same analogy with the AM, because it was a limited factor of 2 sidebands. But in wideband FM there is a multiple range of sidebands. You have infinite sidebands, and you have to the requirement increases because of the bandwidth, because of the power, because you know that if you are taking more bandwidth to transmit, your power will be more, your energy energy consumed will be more. So the bandwidth of WBFM is 15 times of that of NVFM. So it is a huge loss of bandwidth and power when it's we are talking about WBFM. Now let's talk about the generation of NVFM and WBFM. So NVFM is basically used in small type of circuits. You just have the need of a signal of an integrator and a DSB modulator, just like that of AM, and you have to provide a carrier signal with a phase shift of 90 degree, and you get your signal. You can see that. Let me show you. So the first signal of the NVFM was same of as the output from this DSB, but the second signal was 90 degree phase shift, and you can see that the carrier was given directly to it. So this is basically a generation of NVFM. In WBFM there are several methods to find the signal of WBFM. So there are two basic methods. The first one is direct method, and the second one is indirect methods, and furthermore there are subclasses of direct method and indirect method. So first let's talk about the direct method. So this direct method basically makes the use of a device or a IC. Basically is this not a device, is basically IC, small IC. This is IC is known as VCO, and this IC is basically already installed in your cell phones. If you take out the layout of your cell phone, you will see that there will be an IC termed as VCO. Mostly back in 2011 I did a project in which I used this VCO. So I basically took out this IC from a local mobile because it was not available on the market. I was searching for a specific IC number of this VCO. So this VCO is basically a frequency generator. This is basically this VCO generates kind of a frequency, because you know that it is oscillator, and oscillator is the inverse of rectifier. You all people know that. So you have to create some kind of frequency, and for that you need a VCO. And mostly this just like this Intel and IBM, there is a company called Maxim which manufactures this VCO. So you can also do your research on that which type of VCO is generating what kind of frequency. So this is a small IC, this is a very tiny IC, so you can also do your homework as well for that VCO. The second method is Velectra method, in which commonly used Velectra diode, or Velectra diode is basically this. It is not Velectra, this is Velectra diode, and you can also do your homework about that, how this Velectra diode basically works. And this is circuit diagram I have shown you, that this is you can see that this is a tank circuit over here, also known as oscillator tuned circuit. You also know that how does this tank circuit work. We have also discussed the tank circuit in the previous class, I hope. Yes. So this is the tank circuit over here, and it is generating some kind of frequency, and that is given to the Velectra diode, and it is second portion is grounded, and this is a transformer over here which is basically providing to you a modulating AF voltage. So this is the Velectra method diode methodology, and this is the indirect method, also known as Armstrong method. There are many furthermore types for the generation of WBFM using different methods, but to keep it to a limited extent, we will just discuss the Armstrong method. So, and this is a huge block diagram, you can see that, and it is also using the same methodology, but it is using some kind of a complex architecture because of humongous sidebands. In fact, if you are dealing with different multiple sidebands, so you will have multiple combining networks, multiple modulators, multiple carriers. So all of these things, and also an amplifier, just because you know that if you are using a multiple and the circuitry is too large, there is a huge loss of power. So before transmitting your data, you have also included a class C amplifier, and you know that I've also taught you about the class A, class B or AB and class C amplifier, and you know that the class C amplifier has the highest efficiency among all of these other power amplifiers. So this amplifier is also placed in the end, because before transmitting the signal, you have to amplify and nullify all the extra noise portion that you want to neglect or negate in the from the circuitry. So this is a indirect method for the generation of WBFM. In the last, we will discuss about the advantages and disadvantages, or you can say the pros and cons of the frequency modulation. The first pro is that it is very much resilient to noise. Mostly when we talked about AM, there was I told you that AM is highly susceptible to noise. It can get corrupted very much easily, because there was a single frequency, and if in that frequency the noise comes, all of the signal is destroyed. It doesn't counter, the amplitude doesn't take any counter effect. But in frequency modulation, because you are varying the frequency, and if there is noise in a single frequency, only the data in that frequency will be destroyed or corrupted. Other frequencies, the data in the other frequencies will remain the same as it is. So it is somewhat quietly good as compared to the amplitude modulation, where it comes to the counter effect of the noise. The second one is it has a strong signal strength ratios, so the variations will be very much resilient, and it does not require any linear amplifier in the transmitter. Our class C amplifier was there, but because of that WBFM, because you want, if your circuitry is very much that is not a linear amplifier, I just told you, that is a power amplifier. And in the last, there is a higher, greater efficiency of this modulation, has a high efficiency as compared to the that of AM and any type of AM. But there are several disadvantages, but the only disadvantage which I see is the power. It has complexity level can be reduced to some extent. because of the loss of the power due to the extent of the sidebands, you have a humongous amount of power that is lost. So some other modes have higher data spectral efficiency. Sidebands extend to infinity either side, so there is a huge loss of power. So these are some things that you need to cater, and I hope that this was all for today. Okay. I hope that you have learned quite a lot in this lecture, and if you have any question, you can write it down, because you can forget it before coming to the class. So you have to write it down on a paper, and make sure that you ask that question, or any confusion. If you face any confusion, you can bring it to the class as well. I look forward to see you in the class, and I will be very much happy if you bring any kind of questions regarding this lecture, because you know that the more you ask, the more you learn. Thank you very much. I'll see you in the class. Allah Hafiz.